Hello, students. This is Shakil, Physics IGCSE O and A levels teacher. I welcome you all in today's lesson, and today we're going to study something about electromagnetic induction. This is really important and technical topic from IGCSE Physics, and well, the applications of this topic are AC generators and transformers, and these two are essential ingredients of our electrical distribution and production system. So let's look at the syllabus points from this chapter. Well, first point from electromagnetic induction is knowing the fact that when a conductor is moving across a magnetic field or a changing magnetic field link a conductor, then it induces an EMF in the conductor. EMF is actually the voltage. And then we'll be looking upon doing some experiments to demonstrate the electromagnetic induction, that how we can produce EMF or voltage or current in a conductor which is placed in a changing magnetic field. And then we'll be telling the factors to increase the magnitude of induced EMF. And then in the supplement, in the advanced topics, we will look upon some of the technical things, such as to know that the direction of induced EMF opposes the change causing it, and then state the use of relative direction of force, field, and induced current. Okay, the next will be the AC generator and the transformer. Okay, so let's look upon electromagnetic induction. So first of all, we have a pair of magnetic poles. So these are magnetic poles. And these are producing uniform magnetic field, which is pointing from north to south in these arrows. Okay, then a wire is held between the magnetic field, and then there is an ammeter. That ammeter is used to measure the current. And this is a center zero ammeter. Let's say the zero is at the center and one side is positive and other side is negative. Okay, what we're going to do is, like, remember, there's no battery in it. What we're going to do is we move the wire in upward direction. So when we move the wire in upward direction, it experiences a changing magnetic field, like the magnetic field lines linking the wire are going to change, and this will result a deflection in ammeter. It means that in the wire, if you want to produce current or voltage, you have to move that wire inside a uniform magnetic field. So if electrical conductor cuts through magnetic field lines, a voltage is induced across the ends of the conductor. If the wire is part of complete circuit, a current is also induced. So two important things are there. The first thing is the voltage induction, and the second thing is current. So if you are only moving the conductor inside the magnetic field, then only voltage will be induced. So I can draw it like this. Let's say this is north and this is south, and then the wire is there, and you're only moving this wire, which is not part of the complete circuit. You're moving it up or down. So what's going to happen is both the ends, one end will be at negative potential, the other one will be at positive potential. So we say that voltage is being induced in this wire when you move a simple wire in a magnetic field. But if this wire is part of a complete circuit, like the way shown in the diagram, you can see that the man who is holding the wire, and this wire is part of a complete circuit. How it is complete circuit? Because the wire is connected with the ammeter. It is making a closed loop. Complete circuit means closed loop. Wire is connected everywhere. Closed loop. So then it will induce current in it. Okay, so this effect is known as electromagnetic induction, and sometimes it is also known as generator effect. So it means that whenever you move a conductor in a magnetic field, then it induces a voltage in the conductor. This effect is known as electromagnetic induction. Or whenever you move a wire, which is part of the complete circuit, let's say a ammeter is there or a resistor is there with the wire, and you're moving that wire inside the magnetic field, and wire is form of the complete circuit, then current will be induced. So this process is known as electromagnetic induction. So here is another example for this. We have a coil. This is coil of wire. And then both these ends are connected to a voltmeter now. This time it is connected to voltmeter. Okay, so now a magnet is held at rest over here. And when you're going to drop the magnet and the magnet is going to pass through the coil and it's going to move downward, then moving magnet produces changing magnetic field, and then a voltage will be observed on the voltmeter. So if a magnet is moved in the coil of wire, a voltage is induced across the ends of the coil. If the direction of motion or polarity of the magnet is reversed, then the direction of induced voltage and the induced current are also reversed. We'll also see this in the factors, that how you can reverse the polarity of induced current or polarity of voltage. We can do that by reversing the polarity of the magnet. So electromagnetic induction also occurs if the magnetic field is stationary and coil is moving. Like you have to move one thing, you have to move the magnet or you have to move the wire. So if we look back over here, you are moving like the magnets were stationary and the wire was moving. So when the wire moves in the magnetic field lines linking the wire changes and it induces voltage and current. On the other hand, if the coil is at rest and magnet is moving, again the same effect happens. It induces EMF or voltage. So the thing is, one of them should move. Either the wire should move or the magnet should move. Okay, now how to increase the size of this induced voltage? Like you have to produce more voltage. So the first thing is quite obvious. You have to increase the movement. You have to increase the speed. Increase the speed of rotation of the wire. Move the wire quickly. Then strength of the magnetic field, like you have to use stronger magnets, and then you have to increase the number of turns of the coil if the coil is there. So that would increase the amount of induced voltage. And of course, the area of the coil is greater, bigger size area of the coil is required. Okay, so now some handwritten important exam notes. First of all, we are going to define the electromagnetic induction. So it is the process of inducing or producing voltage or EMF in a conductor due to linking of changing magnetic field is known as electromagnetic induction. So that's how we define this electromagnetic induction. This definition comes for 2 marks. So you have to learn this word by word. It is the process of inducing voltage in a conductor due to linking of changing magnetic flux. Okay, there are some points to remember. The first point is EMF and voltage is produced when a conductor is moved inside a magnetic field. Okay, second, current is produced when conductor is part of complete circuit. Like if the wire is complete, it is in the form of a loop, then current is also produced. And number 3, EMF or current can also be induced if magnetic field changes and conductor remains at rest. We have studied that previously. Okay, before we move forward to the next topic, I want to demonstrate something to you. Okay, so let's say this is a magnet. So we can see that it is having these magnetic fields. Magnetic fields always go out from the North Pole and they go into the South. Okay, we can reverse the polarity as well. So now the first case is when the magnet is at rest. Then this is the coil of wire and it is connected to a lamp. There is no battery connected with it. So you can see that when the magnet is at rest, constant number of magnetic field lines are linking the coil, like the white lines 1, 2, 3, and 4. 4 lines are linking. As the magnet is not moving and coil is not moving, so there would be no current or voltage produced as the lamp is off. And remember, this coil is part of the complete circuit since its both ends are connected to a lamp. So it is forming a closed loop, closed circuit. So we say that current will also induce in it. Now, if you want to see the effect, I'm going to connect a voltmeter with the lamp. So you can see this is a center 0 voltmeter over there. the pointer is at 0, it means no voltage is produced. One side is positive, one side is negative. So you have to see carefully. I'm going to move the magnet towards the coil. So you have to see what will happen. Okay, you can see that the pointer was deflecting towards the negative end. I'm going to repeat this process again. Okay, I'm going to take the magnet towards the coil. So you have to see that in which direction the voltmeter is going to deflect. So it's deflected towards the negative side. So it means that when you are moving the magnet, it means that, okay, so you can see from here that when I am moving the magnet towards the coil, changing magnetic field lines are linking the coil, so that induces voltage and current in the coil. But the important thing is that while moving the magnet towards the coil, the voltmeter shows the voltage towards negative side only. But if I take it back, the voltage are towards positive. Go in, negative, go out, positive. But if I keep moving towards and away, so you can see what's going to happen. You can see the coil is under the influence of changing magnetic field and voltage are producing both way. So this tells us one thing, that if a magnet is moving towards the coil, it produces voltage, let's say negative voltage, because voltmeter is showing the negative reading. But if you're moving the same pole away, then the voltage produced are positive. So this means that if you want to produce only the DC voltage, then move the magnet towards the coil or away from the coil. But if you want to produce AC voltage, then you have to keep moving the coil towards and away from it, like this. So you can see that the deflection is both way. Deflection is both way. But only moving towards the coil, deflection is one way. Only moving it away, the deflection is other way. Okay, you can reverse the polarity of the magnet as well. So what thing we are moving? We are moving the magnet to produce changing magnetic field. The coil is at rest. And now we can do one more thing. We can reverse the polarity of the magnet. See? And still it is producing voltage. See? Positive, negative, positive, negative. Why? Because we are continuously changing the polarity of the magnet. Okay, now if we use two coils, so the top coil is having only two turns. So you can see that less voltage are produced. The bottom one is having 4. So if I move it at the same speed, you can see more voltage are being produced. So this is one of the factor. If you increase the number of turns, you will get more voltage. Okay, now we have to move to laws of electromagnetic induction. There are two laws of electromagnetic induction. One of them is Faraday's law and the other one is Lenz's law. So let's look upon Faraday's law first. Okay, so the thing is, Faraday's law states that the amount of induced EMF is directly proportional to rate of change of magnetic flux linking the conductor. And flux here means group or bunch of magnetic field lines. So instead of using the word magnetic field lines, we use the word magnetic flux, like bunch of magnetic field lines. So Faraday proposed that the amount of induced EMF or the voltage that are being produced in the conductor or coil is directly proportional to rate of change in magnetic flux. It means if the magnetic flux is changing quickly, which can be done by moving the magnet faster or moving the coil faster or moving the wire faster, then you can get higher value of induced EMF or voltage. Okay, so second is Lenz's law. Lenz's law is again a famous law. It tells us the direction of induced current is always such as to oppose the change in magnetic flux producing it. Or we can say that the induced voltage or EMF polarity on the conductor always opposes the cause producing it. This is a strange law, but it is in accordance with the law of conservation of energy. And it states that the induced current always flow in a direction that uh, such that it opposes the change which produce it. Okay, so I was telling you about the lenses law. The statement is very important for both these laws. Like the Faraday law statement is this one, you need to memorize it. The amount of induced EMF is directly proportional to rate of change of magnetic flux linking the conductor. And for the lenses law, it states that the direction of induced current is always such as to oppose the change in magnetic flux producing it. And its description is very simple. You can see here there is a coil and it is connected to a galvanometer. Or it is the sensitive ammeter actually. So what is being done is a north pole is being moved towards the coil. So when the north pole is going to move towards the coil, a changing magnetic flux is going to link the coil. So as a result, it induces the current in the coil. Now the current, when the current will flow in the coil, it will make the coil an electromagnet, because whenever current flows through a coil, the coil becomes electromagnet. So and that coil is actually equivalent to a bar magnet, which is having north and south pole. So this coil, which is in which the current is produced, become a magnet. So it will have two poles, north and south. So in order to know that which side is north and which side is south, we will use Lenz's law. So Lenz's law tell us that induced current in the coil is always flowing in a direction such that it opposes the change with producing it. So what is the change? What is the cause that is producing the current in the coil? The cause is the moving magnet. So moving magnet is the cause actually. So the coil has to move, has to stop that. So the magnet can be stopped if the coil is electromagnet and similar poles will be induced at the end of the coil, which is near to the magnet, which is a north pole, and the other one is the south pole. So if this happens, only then the moving magnet, which is the cause, can be stopped. So after that, we can use right hand grip rule to identify the direction of induced current. So you will hold the coil in your right hand, you will point your thumb towards the north pole, and then the curl of fingers will tell you the direction of the induced current in the coil. Okay, in the second diagram, the north pole is being pulled away. So when it is pulled away, it also links the changing magnetic field lines to the coil, causing induced current in the coil. Now the thing is that induced current will make the coil as a magnet. The coil becomes a magnet, and it has to oppose the change or the cause which is producing it. So the cause here is a moving magnet which is moving away now. So coil has to stop it. Coil has to stop the magnet. So this can be stopped only if south pole induces here, like south pole of the coil induces here, because opposite poles attract each other. So the other end will be north pole now, and again you will use right hand grip rule. Hold the coil in your right hand, point your thumb towards the north pole, and then the rotation of the fingers tell you that the current in the coil is moving downward. So that's how uh, you can tell about the direction of induced current in the coil. It is important to see that in the first case, when the coil is moving towards the coil, the galvanometer shows deflection to one side, because this is a center zero galvanometer. The zero is at the center. So the blue needle is towards the positive. But if the magnet is moving away in the second case, then you can clearly see that the current direction changes and the galvanometer shows direction reading in the negative side. Okay, So how to find the direction of induced current in the conductor? I've written everything over here as well. So first of all, you are going to use Fleming's right hand rule here. So you're going to use Fleming's right hand rule. Why right? Because you know right, I, RI, and I is the symbol for current. And you know Fleming's left hand rule, in that F is the symbol of force. So that's why Fleming's left hand rule is used to find direction of force on a current carrying wire placed in magnetic field. And Fleming's right hand rule is used to find direction of induced current in the magnetic field. So everything is there. You have to use your right hand and you have to point thumb towards direction of movement or direction of force in the coil. You have to point your first finger towards direction of magnetic field, which is always from north to south. And then the second finger will tell you result, like it will tell you the direction of induced current, which is the conventional current. So Fleming's right hand rule is used to find induced current direction in a conductor when it experiences a changing magnetic field. And here is the method how you're going to use it. You have to use your right hand. You have to point your thumb. This is the first point. You have to point your thumb towards the force direction or direction of motion of the conductor. You can apply this while watching the video on the diagram, which is drawn here. You can see that the direction of force is downward. So take your right hand, FBI, and point thumb downwards. Point thumb downwards. Okay, thumbs down. Okay, that's what happened when your favorite team is losing the match. So you will point your thumb in downward direction, but if your favorite team is winning, your thumb is always in the upward direction. Okay, that was a sideline joke. So let's get to the point. You have to point your right hand thumb downwards since the force is downward, right? So point your thumbs downwards. That's really interesting. Let's see what's going to happen. Okay, the second thing is you have to point your first finger towards the magnetic field direction, which is always from north to south, like this way. So point your thumb downward, point your first finger from north to south, and then the second finger, the middle finger, will be pointing towards direction of induced current, and which I hope you are getting in this direction. Like the current is moving in this direction. So when current goes in this direction, it means pointer is going to deflect this way. So that's how you can find direction of induced current in this conductor. So if you want to change the induced current direction, there are two ways. You have to change the direction of force on the conductor. Like first, the force was in downward direction. So if you apply force in upward direction, so this will reverse the direction of induced current. The second is, if you don't want to change the direction of force, you have to swipe the poles. So you can do these two things to change the direction of induced current. Secondly, how to increase or decrease the induced current or voltage in the conductor, like the factors. So the first factor is changing the magnetic pole strength or their size. And if you use stronger magnet, more voltage will be induced. And number two is change the speed of conductor or amount of force. So if you move the conductor faster, it means you will be getting more voltage. Okay, so these were the points. Now let's do some of the past paper questions. Okay, let's look upon the first question. This is the solenoid connected with ammeter, and this is a rod. So they're saying that a solenoid is connected to a very sensitive ammeter, which is actually a galvanometer. A rod is inserted into one end of the solenoid. The ammeter shows that a small electric current in the solenoid while the rod is moving. It means while the rod is moving, the ammeter is showing the current. It means the rod is magnet, definitely, because if it is magnet, only then it can be producing changing magnetic field lines. So only then current can be induced, because electromagnetic induction is the process of inducing current in a coil or wire when it experiences a changing magnetic field. So which rod is being inserted? A heated copper rod? No. A magnetized steel rod? Yeah, it means it is a magnet actually. So yeah, these are option. An uncharged nylon rod? No. A radioactive uranium rod? No. So whenever you move a magnet, towards or away from the coil, then it produces a changing magnetic field, and hence voltage or current are being produced. Okay, let's look upon the second one. There is electromagnet. This is the coil on the iron core. This is a switch, and this is the battery, the DC battery, of course. And then there is another coil, the soft iron core, and this is the voltmeter. So the diagram shows an electromagnet near a coil of wire connected to a voltmeter. The reading on the voltmeter is 0. So still the reading is 0. It means no voltage are produced. The switch is closed. This switch is going to be closed now. The electromagnet magnetizes quickly. Of course, current from here is flowing this way. And if you use the right hand grip rule, point your fingers towards the flow of current in the electromagnet and stretch your thumb. So it means this is north and this is south. What happens to the reading on the voltmeter? Okay, when the switch is closed, what happens to the voltmeter? When the switch is closed, the current value goes from 0 to maximum. And this means that current is changing. So when current is changing, then you know that magnetic field also changes. So when a changing magnetic field links the soft iron of the coil, it produces a voltage in that coil. So we say that what happens to the reading on voltmeter? It keeps increasing. Okay, maybe. It quickly increases and stays at maximum. No, it quickly increases and then decreases. It can happen. It always on 0. No. So you have to choose two options from A and C. It keeps increasing. So when you closes the switch, what happens? The current goes from 0 to maximum, and after some time it becomes maximum, like constant. So constant current produces constant magnetic field, and when the magnetic field is constant, it means voltmeter are not going to show you the reading. So that's why your option is C. It quickly increases and then decreases. Why decreases? Because when you close the switch, current goes from 0 to maximum, and when it goes from 0 to maximum, it is actually changing. So changing current produces changing magnetic field. And when the current becomes maximum, it becomes constant as well. So constant current doesn't produce changing magnetic field. So that's why voltmeter reading increases. Okay, the next thing is this is a wire which is connected with a resistor. A current is induced in the direction shown, in which direction the wire is moved. Okay, so the induced current flows this way. The magnetic field is from north to south. They are saying that which way the wire is going to move. Okay, so we can apply Fleming's right hand rule here. Fleming's right hand rule. So let's apply the rule. Take out your right hand and point the first finger, which is towards the magnetic field. So point it from north to south, and then point your second finger towards flow of current, which is like towards you. So you can clearly see that the thumb is pointing in downward direction. So again, apply the rule. Point your first finger towards the magnetic field like this way, and point your second finger like in this direction. And both of them should be of your right hand. So when you do this, you can clearly see that the thumb is in downward direction. So your answer is C. Okay, next, the north pole of a magnet is moved into the coil of wire connected with a galvanometer. Okay, it is connected through it. This is galvanometer or sensitive ammeter. The needle of the galvanometer moves. Which situation must give a smaller galvanometer reading? A smaller. Okay, so there are the factors. Of course, the number of turns of the coil, the speed of magnet, the strength of magnet, that is important. So use a coil with fewer turns and a stronger magnet. Fewer turns is fine, but stronger magnet is not okay. Use a coil with fewer turns, yes, and a weaker magnet, yes. So this is the answer. Use a coil with more turns, no, and stronger magnet, no. Use a coil with more turns, no, and a weaker magnet, yes. So it means your option is B. So it means that the factors that can affect the EMF is number of turns of coil, number 2 is strength of magnet, and number 3 is speed of magnet. So these are the factors for induced EMF. Okay, let's look upon some theory question now. Figure shows a magnet that is held at rest just before the vertical coil connected to the galvanometer. Okay, the magnet is released. It means it is going to move down. State any effect on the galvanometer. State. So this is of 2 marks. So obviously, when you are holding it at rest, the magnetic field which is linking the coil is not changing. So it means the galvanometer will show you no reading. But once the magnet is moving down, the change due to its movement, changing magnetic field is going to link the coil. As a result, current will be induced in that. So we say that when magnet is released, it causes changing magnetic flux linking the coil. This will result in production of EMF and current. So galvanometer shows deflection in one direction. Since the magnet is moving only in one direction, so galvanometer will show a continuous deflection to one side. Okay, state any effect on the magnetic field produced by the coil. So when the magnet is moving, then there is a current that is being produced in the coil. Of course, the current is going to produce in the coil. So that current will also produce. Okay, hold on. Okay, I was explaining, this thing. So the thing is, when current will induce to the coil, it produces a changing magnetic field. But as you can see that the current produced is not permanent, the current induced is also changing, so it will produce a changing magnetic field. So we say as induced current varies in magnitude, so it will produce varying magnetic field. Like as the amount of current changes, of course, the magnetic field also changes. Okay, the last question. A bar magnet is held with north pole just at the one end of the coil. Okay, figure shows the coil connected to a galvanometer. Again, it's the same thing. The magnet is pulled horizontally to the right. Okay, it is pulled to the right, this side, through with constant speed through a large distance. Okay, so constant speed to a large distance. State what happens to the galvanometer reading as time passes. Okay, so as it is moving away with constant speed, so it means the galvanometer reading will show the deflection, because when the magnet is moving, the magnetic field is changing. You can answer yourself. The answer is when the magnet is moving away, it produces changing magnetic field as the magnet is moving at constant speed. So the magnetic field changes uniformly. So this would cause induced current, which changes gradually from a maximum value to a minimum value. And then number 2, as the magnet moves, the north pole is produced at the left hand end of the coil. Explain why the pole at left is north. So they're saying that at left, north pole is there. It means over here will be the south pole. So they're saying why on the left north pole produces. So we'll say that we have studied this as in Lenz's law. According to Lenz's law, whenever a current is produced due to changing magnetic field in the coil, the current direction will be such as to oppose the cause producing it. And the cause here is moving magnet, which is moving away. So you need to stop it. So if you want to stop a moving magnet away, you need to induce opposite pole. So if south pole will be induced here, only then it can stop the moving magnet. So thank you, students. I hope things are good for you in this video. I'm going to share the second video soon, in which we'll discuss the applications of electromagnetic induction, that is the AC generator and transformer. Up till then, take care, everyone.